Alright, I'm going to talk now about an algorithm called Quicksort. Sounds like it should be pretty quick, right? But is it actually as quick or quicker than merge sort? Well, we'll find out by the end of this video. Okay. So, Quicksort is another recursive algorithm, another divide and conquer algorithm, but it goes about things slightly differently from merge sort. So here are the main steps at a high level. So Quicksort crucially relies on something called a pivot. So we pick a pivot in the array, which is just some element. Although it does depend, which element you choose really does impact the efficiency. But for now, we'll just make it some element in the array. Then what we want to do is move all elements less than the pivot to the left side. And move all elements greater than the pivot to the right side. I guess we could say greater than or equal to the pivot to the right side. Okay? And then here's where the recursion comes in. We recursively sort the left elements, and then we recursively sort the right elements. Okay, so let's put this into action on this example of an array down here. So let me say that I'm going to actually choose the pivot to be the last one. So I'll just modify this algorithm slightly to say, suppose the pivot is always the last element. Okay. Alright, so what I want to do is walk through this array, and I'll do something like, for the moment, I'll do something like what I did in merge sort, where I have an auxiliary array where I can arrange things, although I will improve that in a moment. But right now, okay, so we're going to create an auxiliary array, we're going to copy things into it, let me go left to right. So here's my pivot. So I guess what I'll do is I'll have two pointers here. One is to the end of an auxiliary array that has the same length, and one is to the beginning. So let me go through here, and so this is my pivot. You know what, I should probably just pull this off here to the side so we have it as a reference. But okay, so here is the beginning, and here is the end of my auxiliary array. Okay, and then I'm going to just move from left to right here, and I say, okay, is this less than the pivot? No, so it should go on the right side. Alright, so we'll put it over here on the right. And then we'll move this space over one. Okay, now let me move over here. Is this less than the pivot? Yes, so I'll copy it over on the left side. I move over here. Is this less than the pivot? It is, yes, so I'll copy this over here. Is this less than the pivot? Yes, I'll copy this over here. Is this less than the pivot? Absolutely, so I'll copy that over here. And so anyway, every time I'm moving my little pointer here. Is this less than the pivot? No, so I'm going to copy this into the space on the right, actually. Move the right over. Okay, is this less than the pivot? Nope, so I'm going to copy that onto the right side. Is this less than the pivot? Yes, so I'm going to copy that onto the left side. Is this less than the pivot? Yes. So I'm going to copy that onto the left side. And then finally, we actually have the pivot, which we'll put here. Okay. So what you have is actually, we've split this up into two parts. Everything on the left side is less than this pivot here. So let me put this is the height of the pivot here. So everything on the left side is less than the pivot, and everything on the right side is greater than the pivot. So if we manage to sort the left side independently, and we manage to sort the right side independently, then we will have sorted the whole thing. So that's where the recursion kicks in. Alright, so let's look at some code that actually implements this. So the first step is to choose this pivot. And we might as well just choose the element at the end of the array to be the pivot. So I'll say pivot equals array at index -1. So that's the last element. Okay, now I need to move all the elements less than the pivot to the left side and move all the elements greater than or equal to the pivot to the right side. Let me actually do something that's a little bit less efficient, but that makes the code very, very short. So I'm going to say left is equal to x for x in array if x is less than pivot. Then I'm going to say equals x for x in array if x is equal to the pivot. And then I'll say right equals x for x in array if x is greater than pivot. Okay, so I'm using something here called a list comprehension in Python. It's a way of making a list out of a list. It's kind of interesting. It's very succinct syntax for doing this. Let me just show you how it works really quick. So if I I make some random array. So I'll print out the array. And let me just have a look at what these lists are. So the pivot in this random array should be 28. I'm picking the last element. So if I print out the left, I should see everything less than 28. If I print out the equal, are there any elements here equal to 28? I don't see any, so it should be empty. And then if I print out right, it should be everything greater than... Oh no, there is 128 in there. Where is it? Oh yeah, well duh, it's the pivot. Okay. Okay, so other than that, all right. So this actually would create 3 different lists, and it was very quick. The problem is when we say for x in array, this is actually looping through every element in the array. So technically, we're looping through the array 3 times to create these lists. So that's not great. And we're also creating these lists on the fly, which are array lists in the background. Sometimes they have to do this doubling, but we know the amortized cost isn't too bad. Okay, whatever. All right, so then what we can do is we can actually use this nice list concatenation feature in Python. We can say that, well actually, okay, I need to sort these first. So I'm going to have Quicksort return an array. So I'll say left is actually equal to Quicksort left. So we need to recursively, so that was step 3. We need to recursively sort the left part. We need to recursively sort the right part. And once we've done that, now we can put them all together. So we can say return left plus equal plus right. So this is really, really short code to do Quicksort, which is cool. And it uses recursion. Okay. So let's see if it works. I mean, maybe it's cool, but it doesn't work. Does it actually work? So I'll print out the array, then I'll do, I'll say array, and I'll just actually print Quicksort array. So let's see. We'll first have to run that code. Let's see, what did I mess up? Ah, I forgot the base case. Nobody told me. Okay. So the base case is if the array I passed along is length 1. Right? Or 0. So I'll say less than or equal to 1. Then I just return the array, right? Or actually, you know what? I'll just do nothing. Oh no, but I do need to return something. Okay. We're not supposed to return to more than one place, but let's just do it here. Okay. Otherwise, we'll do the recursion. Okay. Now that did it. Okay, cool. So that sorted it. Now, so far, in terms of memory, this is no better than the merge sort, really, because I still have to have this auxiliary structure. So it turns out we can actually do something called an in-place quicksort. And I'm just going to show the code here. I don't want to dwell on it too much, but I wrote this ahead of time. So here's some code that will accomplish this without having to make another array, just by moving things around. If I can swap elements in the array that I have, this will actually go through and swap them. So it chooses the pivot to be the rightmost element, and then it loops through and it puts things in place without having to copy them to another array. And then it does the recursion. Okay, so one advantage this has over merge sort, this version, is that it doesn't need an auxiliary array. So it doesn't need any extra memory for a staging area. Okay, so that's nice. Again, let me just show you that this works. So this is a new version of Quicksort I have now. Oh, and because it sorts it in place, I'm not actually returning something after I run Quicksort. the array should be sorted in place. So if I print it out after I run that, then it should be, yep, okay, so that works. But this, it's doing the same thing. It's picking a pivot and it's arranging elements in place now. So it's changing elements in this array around so that they're in an order. Where all the elements that are smaller than the pivot are to the left and all the elements that are larger than the pivot are to the right. Okay, now I want you to look at the results of an experiment that I've done with both merge sort and quicksort, and I want you to make an observation. And I know I told you I was going to tell you about the complexity of quicksort now, but let's just take a moment to see how it runs, and then I'll talk about the complexity.